Welcome to the lecture series on solar power systems. In our previous video lecture, we were on phase 1, the lecture number 1. So welcome to the lecture number 2 of the phase 1. This is yet going to be another important lecture of this phase. In this lecture, we are going to study what is meant by solar PV cell, what is meant by PV array, what is the difference between cell and the array, what are the properties of a photovoltaic cell, and the power curve, what is the power curve, what is the IV curve of a solar cell, and then a solar array. Or also one more thing to discuss is the solar PV cell. Then what is mean by PV module? These three things are mostly used: the solar cell, the solar module, and the solar array. You should understand the difference between all of them. What are the cell properties, and the detailed understanding of this we will be covering. Let me move to the computer screen. Okay. So what is meant by solar cell? Now this is, in this figure you can see here, this is the PV cell. Okay, the individual cell, the individual PV cell which is generating around 0.5 volt. Okay, now, and this is what, which is you can see everywhere. This is the solar panel. You say it a solar panel. Now this solar panel actually comprises of many cells, thousands of cells or hundreds of cells. Sorry, I must say hundreds of cells are there in a one PV panel, also known as the photovoltaic module. And here you can see on the rooftop there are more than one solar panels. 1, 2, 3, 4, 5, 6. 6 in this row, 6 in this row, and 6 in this row. The total of 18 solar panels. And they are actually connected with each other. So this combination is known as the photovoltaic array. Understand the difference. What is the cell? The cells, different cells are combined in parallel and series to make a module, also known as the PV array. Sorry, the PV panel or the PV module. And then you have several modules are connected in parallel and in series to form the PV array. One more thing to understand here is the panel quality. You have A grade panels, B grade panels, or C grade panels. This is, what is this grading? Grading means how much the efficient, or wait a minute. So what is meant by grading? Grading means that how much good the material is used in a panel, in a cell, and if the cell is made from the refined materials, then you are going to extract maximum energy from that area in which the panel is installed. And if the cell is of B grade or C grade, then it means that this is more disturbed by the temperature, if the temperature of the area is high, then it means that the panel will not be providing you the much efficiency. So C grade panels are normally, they are cheaper as compared to the A grade panels. And so this is how this grading is done based on the standard testing certificates, standard test. This grading is evaluated. What is this? The watt is equal to volt multiplied by current. This is obviously representing you the power of either a cell or an array or a module. Let's move next. Here there are basic terms about the conversion efficiency of a PV cell. What does it mean? It means that around today's solar cell efficiency is around 17% at max. Now, what is meant by efficiency of the solar cell? It means that, as I told you in the previous lecture, that I shown you a patch of land which was a meter square patch of land, and I told you that you are receiving 1000 watt on this meter square. Okay, so on a patch of land you are receiving 1000 watts at an instant. But if you install or place a solar cell or a solar array under that on that surface, then it will able to extract only 170 watt. Okay, this is meant by the efficiency of the solar cell. Let me explain you again. This is the patch of land. This is 1 meter square patch of land, and here you have sun. Okay, and the energy you are receiving is around 1000 watts on this patch of land, which is meter square. As I told you, the solar cell efficiency is 17%. What does it means? That you will able to and if you place here the PV panels, then you will able to extract, you can extract around 170 watt, okay, out of this area. Researchers are working on increasing the efficiency of the solar cells. Understand this concept? Okay. Now, what is the module peak power on the solar panels? On the back side, rear side of the panels, this is mentioned. It is what? WP, kilowatt P. What does it mean? Kilowatt peak, the maximum energy the solar module can provide you under these standard conditions. The standard condition, as I told you, what is the solar radius? 1000 watts per meter square. Under that standard condition, what will be the maximum power? The maximum power the panel will able to deliver you. So this is what known as the watt peak. In the upcoming slide, I will showing you the nameplate behind the solar panel. And there are also different factors under ideal conditions, like in the Germany, or as I told you, this maximum output of a PV module. This is in actually the kilowatt hour We discussed it in detail in our lecture number 1 of the phase 1. Okay. Is this recording or not? Yes, it is. Now let's next move to the the performance ratio. It is telling you about the efficiency of the overall systems installed. Now this is not related to the conversion efficiency. The conversion efficiency is a different thing, and performance ratio is a different thing. Performance ratio deals with the energy extracted by the solar panel and the energy lost in our power processing. This is what defined by the performance ratio. Normally, we have around 70 to 80% efficiency reached in our systems. And what is the real power output of a PV module? Obviously, it is in. Now, what is the real output? Now, this is the real kilowatt hour. Actually, a module, let's say if you have a module and it is mentioned that the module is around 50 watt, then how much energy that PV module will provide, it depends on the solar irradiation and solar irradiance. If if it is in Pakistan, then you can get more energy from that similar solar panel. If it is in the Germany, you will be able to get less energy because of the sunlight intensity and the duration of the sunlight which is remaining per day. Okay, so in this lecture, in this slide, there is a idea that this is the silica sand. From that sand, you make silicon blocks, and then you able to make the wafers of the monocrystalline wafers. This is more relevant to the physics theory, and I'm just here giving you a brief or highlighting these things, because if you are more interested in this theory, you can consult a physics course regarding the PV technologies. Okay, the photovoltaic effect. And again, this is actually this slide is telling you that a PV cell is nothing different. It is actually the PN junction. And you guys know what is PN junction. You have P-type material, N-type material, and then a junction is formed there. So what you have here, this is a PN junction, and the N-type material, the P-type material, and you have basically the electrodes on this side. These are the rod type electrodes, and here you have a back electrode which is in the form of plate. Then here you have when the sunlight falls, when the sunlight falls, then the electrons actually flow through the external circuit. So this is what the PV effect. The more details you can find it in physics class. Let us discuss with you the cell types. Well, one of the most important or most used technology is the silicon-based cells, and you know what is silicon, and normally our all power electronics ICs and transistors are made up of silicon. And normally you have either the monocrystalline silicon cells, or you have the polycrystalline silicon cells, which are used in the PV module. And then you may also be familiar with the thin film technology. You might have seen that the solar cells are now becoming transparent and they are installed on the window glasses. So in that thing you have amorphous silicon or copper indium diselenide or cadmium telluride type of cells which are used. So well, the most common type of silicon, the PV cells are made up of either monocrystalline cells or either they are polycrystalline cells. The efficiency of mono or poly are around similar. This is the PV module made up of polycrystalline cells, and you can see this fish-like pattern. If you observe a PV module and this pattern there, then it will actually, because of the polycrystalline technology of manufacturing, and monocrystalline silicon cells are actually plain. There is no pattern on those cells. As far as efficiency is concerned, the polycrystalline silicon cells have less conversion efficiency, while the monocrystalline silicon cells have more conversion efficiency. So that's why monocrystalline based PV modules are more expensive. But on your project, either you use mono or poly, things will work fine. This is the thin film. This is the thin film of the PV, and this here you have flexible. Now this is not the flexible technology, but the thin film manufacturing. Here you don't have the silicon cells, but you have the cells of either this is amorphous silicon or either this is copper indium diselenide or either this is cadmium telluride type. So these silicon cells are more foldable, just like these sheets. So thin film sheets, they are also becoming common nowadays, but the fact is that they occupy more area. Okay, so that's why they are normally but they are used because they have efficiency of around 6 to 8%. So in order to achieve the equivalent power as compared to the poly or monocrystalline cells, and the sheets will be covering more area. These thin film sheets you can observe on the vehicles nowadays because they are much light in weight. They have no weight and flexible, and they are very handy. And this is the future of the PV technology. Now there is a cell type and there is a comparison of different cell types. Like if you have a monocrystalline silicon, its efficiency is around 11 to 16%. This is the conversion efficiency. As I told you that the energy received from the sunlight is more, or I may say the power received from the sunlight is more on the patch of land, but the energy or the power extracted by a PV is less, and this is what this is 11 to 16%. This is the expected area of the module in order to generate 1 kilowatt peak, and this is the module surface area if you are going to generate about 1 megawatt peak. So you can see that if you are using thin film technology or amorphous silicon, the required area of the installation will be more. Once again, if you are interested in getting these slides, email me, I will send you. So here comes another important thing which are pretty used. This is about the electrical characteristics of the PV cells. As you know, what is PV cell? It provides you a voltage and obviously a current. So what are the characteristics on the back side of the PV modules? You can see here. Here, this is the nameplate of the PV module. On this nameplate, one thing is mentioned, the short circuit current, and another thing is open circuit voltage. What is this? Let us understand this. So here you have the properties of PV cells. Obviously, what is the scale of power? Power is actually the current multiplied by the voltage. So if this is the PV cell and this is the sunlight falling on that cell, if you short out your cell, so what the maximum current will flow, because now the resistance is zero. When resistance is zero, the voltage is also zero, because you have just shorten out this cell. Under that case, whatever the current flow is the maximum current, which is known as the short circuit current, ISC. This is related to the one cell. In a PV module, you have more than one cells connected in series and parallel combination. And in a PV array, you have modules, thousands of cells now. So this short circuit current rating is very important. If in any case there a short circuit takes place, then what will happen? A huge blowout can be observed. What is the open circuit voltage? The VOC. Now what you have done, this is the solar cell, you have just made it open. There is no current. The voltage across that cell under the open circuit is known as the open circuit voltage. This open circuit voltage term is important when you are studying the insulation capability of a system. Okay, well, normally the silicon cells have around 0.5 to say 0.6 volts DC when they are open circuit. One more thing is that obviously a solar cell provides you the power, and power is the product of the current and the voltage. Now this voltage is depending on the light. Okay, if there is a light, you will be getting the voltage, but this current is depending on the solar irradiation, because you can do an experiment that if you have a PV panel, uh, take that PV panel under the bring that in your room, and under the normal light like roof light, it will be giving you a voltage, even high voltages. But as soon as you will connect a load and there is no sunlight but your room light, there will be no current flow. But under the sunlight, because the sunlight is which has the maximum energy inside it, under the sunlight the voltage will not drop. Understand what I'm trying to say? I'm trying to say that if you have a PV module, bring inside your room and test the voltage, the open circuit voltage. You may get 12 or 13 volts, but as soon as you connect the load, the voltages will drop to 0 volt, because there is no sunlight but only the roof light which is there, and it has no energy. But if you bring that panel outside under the sunlight, then you will be getting 14 volts or 15 volts. But when you will connect load, the voltages will not drop, because now the sunlight is providing more energy to the cells, and you are running your load. Understand? Okay, so what is open circuit current? Sorry, open circuit voltage, and what is short circuit current? There's nothing difficult in these terms. What's in this slide? The electrical characteristics of PV cells. So here this is a sample specification of the cell number TSMC1 to 5, and these are the dimensions of the cell. The cell is around 1.5 mm by 125 mm, and this is the thickness around 0.2 millimeter. Its efficiency is 17%. This is grade A cell. This cell can produce maximum of 2.52 watt, and its open circuit voltage is 0.617 volts, and the short circuit current is 5.3 ampere. Wow, it's a good current rating because this is the grade A cell. So as I told you that in a PV module you have hundreds of cells connected in series and parallel arrangement, but here we are just analyzing only one cell which has the open circuit voltage of around 0.5 volt. Now here there are two more things, VMP and IMP. What does it mean? VMP means that voltage at maximum power, and IMP means the current at maximum power. What does the maximum power means? As I told you in the previous slide, what is I short circuit? When you are shorting out a cell, the current obtained is what the I short circuit. This is I short circuit. And what is V open circuit? When the cell is open circuit and you are observing the voltage, this is the VOC. Okay. So here you have ISC, the short circuit current, and let's say obviously the VI curve, how VI curve is obtained. The IV curve is obtained by connecting the resistance. What you are gonna do, you are going to, let me show you, this is your PV panel, and what you are going to do, this is what the PV cell. This is PV cell, and here you connect the variable resistance. What you do at the start, you move resistance to 0 value, so the current flow is what the I short circuit, and then you start increasing the resistance. So what happens across this resistance? What you observe? The voltages, the voltage V. Okay, and you keep on increasing the resistance up till the value reaches that at a very high value of the resistance, the current is around 0, such that in the case of the open circuit, the resistance is very high. So at that point, there is no current. Okay, so in this way, we observe this IV curve of this cell. Now, what more information is available here is the maximum. What is mean by the power maximum? Now you know that the power is the product of current multiplied by the voltage. Now there are different instances. What you are doing, you are increasing the value of resistance. Now there appears a point that at that point, let's say resistance is, at that time the resistance is X ohms. At that instant, the product of voltage and current is maximum. And then again, if you are increasing the resistance value, this product is decreasing. Okay, so this is the point at which you are getting maximum power out of this solar cell. That point is known as the maximum power point. The corresponding power curve is shown here. You can see here that at this point, the power you are getting from the solar cell is maximum. So what is done when you are doing the maximum power point tracking? You are pretty much familiar with the the term maximum power point tracking. You may have heard this term. Obviously, you are not familiar because you haven't taken this course before. What is meant by maximum power point tracking? It means that you have an algorithm. You have a solar panel. What you do, your controller or your microprocessor and your sensors, or in short, your controller searches or looks for the point at which you can get maximum power out of this solar cell. This is what known as the point of the maximum power point. This is what known as the maximum power point. So, and this maximum power point is different at different instances of the day. Got the idea of the maximum power point? And one more thing here, it is available that normally for this cell, we observe that at the maximum power point, you can see here, at the maximum power point, the voltage at the maximum power point is 80% of the open circuit voltage. So this cell has the open circuit voltage of 0.617 volts. And the maximum and at the maximum point, at the maximum power point, the voltage is 0.512. Similarly, at the maximum power point, the current is around 95% of the I short circuit. If this is the I short circuit, then this is the 0.95% of the I short circuit. So at the max, so this is what mean by VMP and IMP, that is the voltage and current at the maximum power point. But what happens? This is at the standard test conditions, because this maximum power point doesn't stay at this point. It changes with the time of day. So I think you are understood with this IV curve, that how this IV curve is obtained. I told you, I shown you, in fact, I shown you that here you have a solar cell. Either you are shorting it out, or if it is in the condition of the open circuit condition, so you get ISC, the short circuit current, by doing this, and the open circuit voltage by doing this. This is the point of ISC and this is the point of the VOC. Now what I did, I placed this variable resistor starting from 0 ohms we get the maximum current, and then we started to increase the value of this resistance up till there comes a point that the product of I and V is maximum, and that is known as the maximum power point. And then you have are further increasing the value of the resistance, and what happens is that the product of I and V is less. So what happens in a real time for the maximum power point tracking is that your controller looks for that point and modifies the resistance across the panel in such a way that you that it is ensured that you are getting maximum power out of that panel, because you can see here the voltage is more but the current is less. Okay, so what maximum power point algorithms does, they look for this maximum power point. Okay, so now let's move further. Now, as I told you that this maximum power point, this point is actually depending on the solar irradiation. Now, when we get this irradiation of 1000 watt per meter square, this is at normally at 12 noon, we get irradiation of 1000 watt per meter square. So at that time the maximum power point is located here. If you take an example, right, like around at 3 p.m. during the summer, so the irradiation is at 3 p.m. the irradiation is reduced to around 600 watt per meter square. So at that time of the day, maximum power point is now shifted. Okay, so in the previous slide I shown you that this voltage IMP and VMP based on that cell, this is at the standard conditions of 1000 watt per meter square. But for the rest time of the day, this maximum power point varies. It is not located there. Okay, so this so that's why there's always a need of maximum power point tracking, and this is done by the controllers. So understand the concept of maximum power point. Now look, around 5 p.m. when the sun is about to set, the maximum power point is there at this point. Okay, so how to ensure that you are extracting maximum power out of the solar panel? You need to change the load resistance on the panel. And how this is done? We control the battery charging. The battery charging or the charge current is controlled such that you always get maximum power out of your solar panel. So this is the concept of the maximum power point and the change of maximum power point along the day. So this is the influence or the effect of the temperature change. As I told you that the 25 degrees Celsius is the ambient temperature for a PV cell or PV module to work. But if the temperature increases, what happens? The power which the panel is providing you is decreased. Now look, at 25 degrees Celsius, the curve at 25 degrees Celsius. Here's the curve at 25 degrees Celsius, and here's the maximum power point. Now if the temperature is rise to 35, 45 or 55 degree. Now look, the IV curve is shifted back. Because this curve is shifted, the maximum power point is also shifted. It means that increasing module temperature leads to decreased power output of your solar panel. Oh, this is another important slide. It shows you it is regarding the maintenance. Now look, this is the dust. It is decreasing the efficiency. It is decreasing the efficiency. Now look, this is the solid waste, and it will further reduce your efficiency by 50%. If just 3% of the module surface is covered, if only 3% is covered, then 50% reduction in efficiency. So it is the responsibility of the company or the home owner that you must clean your solar panels regularly. What is this? This is what the PV cell, this is the damage. Whenever you are buying a PV module, ensure that there is nothing type of delamination, because in this way the efficiency of the system or the life of that panel will be much more reduced and it will burn, because it is something the production failure. So always look on this. You must ensure a proper visual inspection. What is this? This is the influence of the shading. Now this is an example of the PV module, and in the boxes this is cells. 1 cell, 2 cell, 3 cell, 4 cell. Now look, this cell is shaded. These shells are shaded. These shells are shaded. So if such type of shade is known as the partial cell shading. Partial cell shading. Each cell is partially shaded. Your efficiency will be reduced by half. This is the example of the full cell shading. The full cell is shaded. The PV module efficiency will reduce to 0. Okay, so you must avoid any type of shade, either your tree or any rooftop shade, because in this way not only the efficiency is reduced, but there is the chances that other cells may burn because of the voltage. What is this? This is this slide is about adjustment. Now you can see this is the tilt angle and this is the azimuthal angle. This is for a specific location that the solar energy capture, that is 100% will be captured if the tilt angle is around 35 degree and the azimuth angle is 0 degrees south. So it depends on the place to place, and charts are available on the internet for each and every locality where you are going to install these solar panels. So what are the influences on the cell? Irradiation, as we told you, the effect of the irradiation, the changing in the irradiation and the changing maximum power point. Then temperature, dust and dirt, shading, direction to sun and tilt angle. Okay. Now this is another important slide about the PV cell interconnection. Now look that here you have 1 cell, 2 cell and 3 cell. The 1 cell, this is the IV curve of the 1 cell, the open circuit voltage of the cell and the short circuit current of the cell. If you are connected connecting these cells in series, what will happen? The total voltage, open circuit voltage will increase and the short circuit current will remain the same. So we connect cells in series in order to increase the voltage. And when you connect cells in parallel, it means that you are increasing the current, but the open circuit voltage is same. So in a one module, you have the cells in series and parallel connection. Okay. So here comes the example, here comes the nameplate reading of the solar panel. On every module, on the back side, you must see either there are certificates available or not. This is the TUV, the testing certificate, IEC certificate, and this symbol shows the proper insulation. And ignore this for the moment. Now looks here, the rated power of that module is 85 watts. The output tolerance means that the variation is 5%. It can be 5% more or less. The short circuit current of that PV module is 5.15 ampere. The open circuit voltage is 22.2 volts. The voltage at P max is 17.8. The current at maximum power point is 4.8. Now this reading is obtained when the irradiation is 1000 watt per meter square. This P max and V max are for 1000 watt per meter square. If the sun intensity is less, it is less than 1000 watt per meter square, then it means that these will not be there. These are the ratings, measurements taken at this standard test condition, and this is 25 degrees Celsius, the temperature AM. Let's ignore this. And the nominal cell temperature was 45 degrees Celsius. This is about the weight. The maximum system voltage, that is if in case 715 volts appear across this panel for a moment, it can sustain. And this is the rating that although its short circuit is 5.15 ampere, but in case if there is somewhere somehow 15 ampere current flows when the voltage is 715 volt due to any short circuit condition, then this can sustain. And these are the standards. What is this? This is the module structure. You have seen the solar panels. So this is what the cover glass, and this is the another layer, and then you have solar cells, and this is the layer which is encapsulating or laminating these solar cells, and this is the cover glass. Again, this is the cover glass. These are the laminations, and these are the solar cells. And then you have a back sheet. Normally it is white, and then you have this aluminum frame. This is the structure of the PV module, and this is the frame at the edge, cover film, the solar cell, and this encapsulation layer, and the back sheet here represented by substrate. Okay, our main aim is that if it is of A grade PV module, then it should last up to 25 years. So if it is a B grade or a C grade, then it means that solar cells are poor and the lamination is not proper. So whenever you are buying a PV module, you must look for these certificates. Now look here. These are the certificates. IEC. This is the certificate of that for the testing and quality certifications. Each solar manufacturing company achieves them after international standard tests. There are many companies which are supplying PV panels without those certificates, and obviously they are C grade companies, or the companies which are not authentic actually. Look, this is the certificate, the license holder, and these certificates are much important when you are buying the PV cells. Oh, look, this is another important thing. Now, whenever you are purchasing a panel, do inspect either if there is the proper sealing or not, because if the sealing is improper, then the lifetime will be reduced, because this improper sealing will poor sealing actually reduce will actually harm the or cause damage to the lamination layer of the solar cells. Now look here, you have excessive glue mark. This is again a defect, and this is a scratch on the glass. There must be nothing such things on the panels if you are purchasing them. So the glass must not be scratched. There must not any excessive glue marks. It means it is repaired, and this is the gap. So visual inspection is very much important. This is what here you have shown, that you are going to connect the panels in series or parallel. So this is one panel, this is one panel, this is one panel, or you can say this is a module, and these modules are connected in series and parallel. Why? Let's see. Let's see if a consumer requires 600 watt and he requires a voltage of 12 volts. What you did, you purchased 6 panels of 100 watt each and connected them in parallel. So in this way you fulfilled his requirement. Now another consumer requires 600 watts, but he requires 24 volts. So what you did, you have connected them in a series parallel combination such that you have obtained not only the 24 volts but also the 600 watt power. So this is what the example of the array design. One more thing, it is requested that, or you must always use the panels of the same type. Same type modules must be used in the PV array. I told you what is PV array. I told you what is PV module. This is for PV module. This is PV module. This is PV module. These modules are connected in series and parallel arrangement. Now look here, you have 6 modules and you have this array, and it must be symmetric. I'm not going to attach a 50 watt panel here, especially when you are having this parallel arrangement, series parallel arrangement. You must look that uh, there must be nothing like the unsymmetry. Now let's have a look on this example. Here, this is an example of the wrong design. Okay, so these are the wrong array selections. Both are wrong. Why? Now look, each panel, now each module is of 12 volts and 4.16 amperes. Now what you done, you have connected here in the way that 4 in the parallel, 4 in the parallel, and 2 in the parallel, and then they are in series. Now what happens, if 4.16 ampere is the current rating of one panel, so these two are connected, so how much current can flow from these two modules? The current flow is 8.33 amperes. Okay, now this module, now what will be the current through this module, through this row? The current through this row is 8.33 ampere. The current through this row will also be 8.33 ampere, because in the series current remains same. Okay, now look, this is another wrong design. Here you have one array, one module here. It has the maximum capacity of 4.16 ampere. So the current in the series will remain same. So how you can correct this design? You need to do what? You need to remove this, because they are extra. They are not playing their role. Now these are extra because you have done the wrong design. Okay, so whenever you are making an array, the array must be symmetrical. Okay, the array must be symmetrical, like 3 cross 3 or 2 cross 2, or like that. And another more thing is that the modules you are using, the modules in an array must be exactly similar. You won't be using a 500 module with a 100-watt module. No, never. Modules must be similar and array must be symmetrical. These are two guidelines which you should know, because you have seen here these 4 modules are not playing their role. Okay, because the weakest element in the connection is limiting the current in the array. Okay, so you can do, if the power consumption is requirement is around 650 volts. Let's say, let me show you one more thing. Let's move to the previous slide. Okay, let's say the customer requirement is this time. The customer requires 750 watt. The customer requires 750 watt. Okay, so and you have 6 panel, you can just increase more panel, but this time the panel must be of 100 watt. Okay, so you will be having one more panel of 100 watt, and let me redraw it. You can have one more panel, and it should be of 100 watts, not the 50 volt. No doubt the customer requires, let's say the customer requires 650 watt. The requirement is now 650 watt. Okay, the requirement is 650 watt, but not the 600 watt. So what you did, you took a panel of another panel of 100 watt, okay, and placed it here. You are not taking the panel of 50 watt. Understand? So all the modules in the array must be similar and the array must be symmetrical. I hope you have understood this concept. Okay. So this is the module number 3 around solar PV system components. We will be covering it in our phase 2. So the lecture number 2 of the phase 1 is now completed. We are now familiar with the basic understandings of the PV cells, the PV array, the PV module, and now we will be starting with the phase 2 of our lectures in the next week.